7.3 CTC Preliminary Analysis. 7.3.1 Initial Taub Generalization. In formulating the closed timelike curve CTC problem, we seek a simple spacetime that in a bounded region admits CTCs. A cylindrical symmetry is desired throughout. Also, it is important that the metric is c-squared, differentiable to second order, so that subsequent calculations with the Riemann tensor are simple. Having decided on such spacetime, we want to know if the weak energy condition is satisfied on the CTC or throughout the spacetime in general. We are also interested in the behavior of the stress-energy tensor at the Cauchy horizon associated with the CTC, especially if the weak energy condition is satisfied.
Before examining the stress-energy problem for CTCs as described above, it is instructive to first consider the Meissner spacetime as example. In the 4D Meissner example, there are competing processes to determine whether or not the stress energy is divergent near the CTC. Classically, there is a blue shifting factor associated with the CTC and a cross-sectional area expansion associated with its repeated projections. The necessary stress-energy divergence is then an indication of positive energy violation. 2D Meissner spacetime instability. 2D Meissner spacetime is a manifold with topology the real numbers double-struct times S, which is a metric space. It will demonstrate some of the distinctive behavior that we must contend with in full 4D spacetime CTC analysis. In particular, closed null geodesic, CNG, instabilities. Here's 2D Meissner. See the next equation. Picture a cylinder to see this.
Figure 7.14. Meissner embed in 2D Minkowski. Let's consider how Meissner embeds in 2D Minkowski spacetime. Consider the coordinate transformation. See the equation shown. We now have 2D Minkowski. See the next equation. The domain 0 is less than or equal to psi is less than or equal to 2 pi. 0 is less than t is less than infinity becomes t is greater than the absolute value of x. In other words, Meissner is covered by the future light cone of 2D Minkowski spacetime. But we have an identification of points due to the periodicity in psi equals psi plus n2 pi. Thus, the points related by boost beta equals hyperbolic tangent of pi are identified. See the equation shown. So, 2D Meissner is the quotient space of the future light cone of 2D Minkowski by the discrete subgroup of the Lorentz group consisting of boosts by beta equals hyperbolic tangent of pi. Meissner spacetime is geodesically incomplete, meaning I can walk right out of this place.
Figure 7.15. Meissner spacetime is geodesically incomplete. Equation 7-68. We have the set of relations, u sub n equals beta u raised to the n minus 1 power, so. Equation 7-69. By rearrangement, which can be done if u sub total is finite. Now to check if finite. See the next equation. Since beta is greater than 1, we have equation 7-70. Thus u sub total is finite, and u sub total equals u sub 1. Note, as indicated in the sketch, there is another way to perform the sum by using the boost relations on variables u and v.
Equation 7-71. Let's shift all of the segments to the same line as shown in the sketch. 1. Boost A to B. U sub 2 equals beta u to the first power. V sub 2 equals alpha v to the first power. 2. Let the Yule ray propagate from B to D. V sub 2 equals v squared. 3. Boost back to original frame. V sub c equals 1 over alpha v squared equals v to the first power. Thus, see the equation shown. And see the next equation. Again summing to get. See the equation shown.
Now consider the implications of an incomplete geodesic, where we reach the boundary of our spacetime, when this is accomplished with an infinite number of boosts. To be specific, consider a packet of energy, a photon say, moving along the incomplete geodesic described. With each identification its energy will be boosted by the beta factor. Thus, in finite parameter distance the energy diverges, and this takes place near the edge of the manifold, the light cone, where the identification is practically that of a closed null geodesic, CNG. This describes the classical instability that is inherent to a spacetime with CNGs.
Unlike the 2D Meissner spacetime, however, In a full four-dimensional theory, we can have defocusing which may conspire to remove the instability. The resulting divergence of null rays, however, is indicative of a weak energy violation. In 4D, does a first CTC, a CNG, have the same blue shifting instability as described in Meissner spacetime? Consider the metric. Equation 7-72. See the next equation. The Minkowski metric in cylindrical coordinates. See the equation shown. Here the light cone has tilted so much that it admits a CNG. If f is less than 0, then CTC occur. Choose f such that for a given observer at rest in the asymptotically flat region, the first CNG is simply. See the next equation.
Now, nabla sub u right arrow equals 0 for a finely parameterized script c, u right arrow equals d script c over d lambda, which can be written in index notation as u to the alpha th power sub semicolon beta u to the beta th power equals 0, and only u to the phi th power is not equal to 0. So, see the equation shown. Thus, equation 7-73. So, in general we have partial differential f of slash partial differential t is not equal to 0, which will then yield the familiar blue shifting instability depending on which way the CNG is traversed, with respect to the sign of partial differential f of slash partial differential t. The relation to Meissner becomes clear if one notes that for certain choices of f the neighborhood of the CNG is
R2 times MISNER. Thus, the CNG in such a spacetime has a similar blue shift divergence to that of Meissner spacetime. A divergence of null rays can counteract this, but this usually implies a divergence of the weak energy condition. Note, however, that from equation 7-74, and in the instance where the vorticity is large, the blue shift may be counteracted without necessitating weak energy violation at the CNG. This is not to say that there isn't still weak energy violation somewhere in the spacetime. To recap where we are so far, the spacetime studied has metric. See the next equation. For which at, see the equation shown,
gives Minkowski spacetime in cylindrical coordinates. And, at f equals 0 we have ds squared equals negative dt rho d phi plus d rho squared plus dz squared. The light cone for f equals 0 has tipped so much that it admits a closed null geodesic. If f goes 0 for some values of its argument, as it does in general, we have closed timelike curves. For ds squared equals negative dt of rho d phi plus d rho squared plus dz squared we have for the future-oriented, pure timelike vector. See the next equation. And the mutually orthogonal spacelike vectors are. See the equation shown.
Let us consider the general null vector, k to the ath power equals t to the ath power plus z to the ath power cosine alpha plus the cosine of beta x to the ath power the sine of beta y to the ath power times sine alpha. In regards to the null convergence condition, our sub ab k to the ath power k to the bth power is greater than or equal to 0. From the Einstein equations, our sub ab minus 1/2 g sub ab of r plus the n area and of g sub ab equals 8 pi t sub ab. This condition implies the weak energy condition.
Let x sub 1 equals alpha, x sub 2 equals sine alpha cosine beta, x sub 3 equals sine alpha sine beta, x sub 1 squared plus x sub 2 squared plus x sub 3 squared equals 1, then. Equation 7-75. Consider x sub 2 equals x sub 3 equals 0, then we have two inequalities corresponding to the x sub 1 equals plus or minus 1 cases. Equation 7-76. Thus, even in case b equals 0 we must still satisfy a plus h is greater than or equal to 0 over bar. Equation 7-77. After a wee bit of work this is equation 7-78.
In order for our spacetime to be asymptotically flat, we must have f of rho right arrow infinity equals 1. For well-definedness at rho equals 0, we must also have f of rho right arrow 0 equals 1. To get a CNG or CTC, we must have f of rho sub c equals 0 at some critical rho. It is thus clear from these arguments that condition on the fraction with numerator partial differential f and denominator partial differential rho above cannot be generically satisfied for this class of spacetimes. If we were just interested in satisfying the fraction with numerator partial differential f and denominator partial differential rho condition at the CNG which generates the Cauchy horizon, we would have to adjust f such that only one CNG generates the Cauchy horizon of the later CNGs that might have been part of the Cauchy horizon. Generally half don't satisfy negative. The fraction with numerator partial differential f and denominator partial differential rho is greater than or equal to 0. The one CNG that then defines the Cauchy horizon then has the fraction with numerator partial differential f and denominator partial differential rho equals 0, this being a special limiting case. There is a further restriction in this instance.
On the first CNG we clearly have f equals 0 for which equation 7-79. Thus, in order to get a minima, f equals 0, at rho sub c we must have. See the next equation. Thus, weak energy is satisfied on the single CNG which defines the Cauchy horizon for a very restricted class of f of rho zet. But in general, the weak energy condition is not satisfied throughout the spacetime for the entire class of spacetimes represented by the metric. Preliminary conclusion. A careful analysis will be done on the above, but some preliminary conclusions are now apparent. Macroscopic CTCs require weak energy violation, agreeing with the chronology protection conjecture. 7.3.2.10.3 redo. Consider a metric that admits CTCs only at a particular instant in a small toroidal region. Also want the metric to be c² so that subsequent calculations with Riemann are possible. So, want a function f of rho z such that at a particular z we have
Figure 7.16. A toroidal CTC region. Since the metric is toroidal, we have a rho squared plus z squared factor, so consider equation 7-80. This function is c². Only want CTCs at a particular instant and want the transition to be at least c². Let's compare a metric that admits toroidal CTCs with Minkowski. Normal Minkowski. Equation 7-81. Toroidal. Increasing phi null geodesic. Equation 7-82. Given the above, for the region to exist for only a finite time, we need to let alpha be a function of t. There is the following possibility. See the equation shown, which simplifies to equation 7-83. Here's a sketch of the light cones.
Figure 7.17. Light cones in the tan3 CTC spacetime. The Cauchy horizon exists for the absolute value of t is less than t sub 0 in the region open bracket rho minus rho sub 0 close bracket squared plus z squared is less than alpha squared. The first CTC occurs at t equals negative t sub 0, rho equals rho sub 0, and z equals 0. Figure 7.18. Winding on to first CTC in tan3 spacetime. 7.3.3 Blues shift analysis for tan3. Let's start from the cylindrical spacetime. Equation 7-84. Where? Equation 7-85. Normal Minkowski in cylindrical coordinates has ds squared equals dt squared minus d rho squared minus dz squared minus rho d phi squared, while the above metric admits toroidal CNGs, actually null ds squared equals dt of rho d phi minus d rho squared minus dz squared. The first CTC CNG occurs at t equals negative alpha, rho equals rho sub 0, z equals 0.
Now that we've identified the curve of interest, we would like to calculate the tangent vector of the CTC as it is parallel transported about the CTC to its starting point, so as to extract the blue shift factor on one loop. Let's call the curve of interest E of phi, where t equals negative alpha, rho equals rho sub 0, z equals 0. Let's derive the normal gamma prime s times and d times r prime s to proceed. Note u equals de of phi over d phi times and d nabla sub u equals 0. Equation 7-86.
Only non-zero is u to the phi th power. Recall in coordinates t, rho z, phi u to the phi th power equals the fraction with numerator partial differential sign with over it and denominator partial differential phi, and u to the beta th power equals the fraction with numerator partial differential e of phi and denominator partial differential x to the beta th power. We now have the curve E of lambda of interest, and it is a geodesic. So consider a coordinate system that set the alpha th power of x of e, then the geodesic equation gives equation 7-87.
As we move along e of lambda for various values of lambda, only the phi th power of x of e of lambda components are changing in the phi t rho z system. So, equation 7-88. The geodesic equation, equation 7-89, then becomes equation 7-90. So what is normal gamma sub phi to the phi th power? Consider, see the next equation, where f equals f of rho z t. We thereby obtain, see the equation shown, and the rest are 0. Now using, see the next equation, we obtain equation 7-91. To proceed we need the mu th nu th power of g sub v gamma equals delta sub gamma to the mu th power, so, let
the mu th nu th power of g equals the 3 by 3 matrix row 1, column 1, a column 2, b column 3, 0 row 2, column 1, c column 2, d column 3, blank row 3, column 1, 0 column 2, blank column 3, negative 1. Need to invert the 2 by 2 matrix row 1, column 1, f column 2, 1/2 times 1 minus f times row 2, column 1, 1/2 times 1 minus f times row column 2, negative f of rho equals the 2 by 2 matrix row 1, ab row 2, bc. See the equation shown. Thus, see the next equation. And we have
the mu th nu th power of g equals the 3 by 3 matrix row 1, column 1, the fraction with numerator negative f of rho squared and denominator negative rho squared times f squared plus 1/4 times 1 minus f squared, column 2, the fraction with numerator negative 1/2 times 1 minus f times rho and denominator negative rho squared times f squared plus 1/2 times 1 minus f squared, column 3, 0 times 0 row 2, column 1, the fraction with numerator negative 1/2 times 1 minus f times rho and denominator negative rho squared times f squared plus 1/2 times 1 minus f squared, column 2, the fraction with numerator f and denominator negative rho squared times f squared plus 1/4 times 1 minus f squared, column 3, 0 times 0 row 3, column 1, 2 lines line 1 o'clock line 2 o'clock column 2, 2 lines line 1 o'clock line 2 o'clock column 3, 2 lines line 1, negative 1 times 0 line 2 o'clock minus 1.
The only the phi th mu th power of g of is times mu equals t, so see the equation shown. And normal gamma sub phi to the phi th power equals 1/2 times 1 minus f over rho times f squared plus 1/2 times 1 minus f squared times 1/2 times negative the fraction with numerator partial differential and denominator partial differential t times negative f of rho squared equals the fraction with numerator 1/4 times 1 minus f times rho and denominator f squared plus 1/2 times 1 minus f squared times the fraction with numerator partial differential f and denominator partial differential t. Equation 7-92.
Consider, specifically, the null geodesic that wins onto the CTC of interest. There exists such a geodesic E of lambda, such that for affine parameter, see the next equation, has in the coordinates phi t rho z, see the equation shown, such that for any epsilon is greater than 0, the absolute value of dt of E of lambda over d lambda is less than epsilon. Same for rho times a n d times z. This follows by definition of the curve that has the CTC as limit curve. That curve being sliced along a given phi and the broken loops arrived at labeled c sub n, such that for every p epsilon CTC, c sub n converges to p. So in such a case we have, see the next equation, where normal gamma sub phi to the phi th power is implicitly evaluated along the E of lambda what has. Equation 7-93.
So f of rho z t equals the hyperbolic tangent cube of rho minus rho sub 0 squared plus z squared plus t squared minus alpha squared, and on the latter marked part, call it x, h of as times x is much less than 1. Now have equation 7-94. Equation 7-95. So, see the equation shown. Thus, equation 7-96. Let see the next equation. And let see the equation shown. Oh, equation 7-97. So, we have a blue shift factor that goes as delta squared for delta small. So, need to evaluate. Equation 7-98.
Where delta sub n equals delta of e of phi plus n 2 pi, rho almost equals rho sub 0, z almost equals 0, t almost equals negative alpha. With delta sub rho equals delta of e vertical bar sub start. Equation 7-99. How is delta sub n plus 1 related to delta sub n? At some time t such that t is less than or equivalent to negative alpha colon delta is much less than 1, we have equation 7-100. We know the absolute value of d phi is much greater than the absolute value of dt, the absolute value of d rho, the absolute value of dz in region. Also the absolute value of dt is greater than the absolute value of d rho times OR times the absolute value of dz, speed of light, c. So, equation 7-101. We want the null geodesic of interest, so see the next equation.
Thus the dominant contribution to the null geodesic curve from dt, d rho times OR times dz comes from dt times as times e right arrow CTC. So times delta almost equals t minus alpha squared over bar. Thus, equation 7-102. And can choose c prime equals 0. Thus, see the equation shown. If we consider the sum on delta sub n squared, we get a divergent result. Equation 7-103. So, the blue shift is divergent.